Today on the Voices of Inorganic Chemistry, we turn the tables and interview the interviewer, Richard Eisenberg. Rich is the Tracy H. Harris Professor of Chemistry at the University of Rochester. He is the 2003 winner of the ACS Award for Distinguished Service to Inorganic Chemistry, and he is the editor of the journal Inorganic Chemistry. My name is Bill Tolman from the University of Minnesota, and I'm here with my friend and colleague, Jim Mayer, from the University of Washington.
Thanks, Bill. Rich, can you start by telling us a little about the early Eisenberg years, growing up, and how you developed an interest in chemistry?
I grew up in New York. I was one of these bulletproof science kids. My interest, though, in chemistry really developed, I think, once I got to college at Columbia. And actually, I think first started in sophomore year. Charlie Dawson was teaching organic chemistry. And I loved the systematization of organic chemistry and how you could build molecules and look at the properties of those molecules relating to the functional groups. Then after that, I had a physical chemistry course with Martin Karplus that was just spectacular. And that really set me on the stage to chemistry. Then I went and did senior research with a young fellow at Columbia who you both know, Harry Gray.
So when did you think you were going to do inorganic chemistry as opposed to the organic and physical that you just mentioned?
It's interesting because I think it relates to Martin Karplus's course. There were two fellow students with me. One was John Alexander, who passed away a number of years ago and was at the University of Cincinnati. Another was a faculty member now at Rockefeller University, Jan Breslow, and we used to do the problems together. And I remember very clearly there was a problem about high spin, low spin. And we didn't have a clue, and we spent hours thinking about it, and it finally clicked in. I said, this is the coolest thing I've ever seen.
Can you talk a little bit about what it was like in Harry's group as an undergraduate and what encouraged you to stay on?
Well, when I decided to do senior research, I went to see Harry. John Alexander was a year ahead of me, and John had started working with Harry on doing theory of metal cyanide complexes, hexacyanometalates. And John said, you really have to go talk with Harry, and I was always intimidated by faculty, but I walked into Harry's office, which was essentially the new assistant professor office. It was right next to an elevator shaft and a janitor closet. And when I walked in December of 1963, Harry looks up and says, Rich, I've been waiting to see you, and we've got some great stuff going. And the rest is history.
Can you tell us a little bit more about the projects that you worked on in that lab and what got you excited about science during that time?
All right. This is, Harry started talking about sandwich compounds. And you know, Harry always used his hands to describe things. And he said, we have these new sandwich compounds, and we're going to make dibenzene vanadium, and we're going to look at its ESR spectrum, and we're going to do calculations and figure out the bonding in this, and we're going to win a Nobel Prize. And then he said, but we need to make dibenzene vanadium first, and let me send you to the lab and talk with Ernie Billig, who was Harry's senior postdoc at the time and a colleague from graduate school with Harry. And that's when I found out that, well, the first thing you have to do is make VCl4, and that we started with V2O5 and carbon tetrachloride vapor in an oven. And if you stop to think about this, we're also making phosgene at the time, and we were venting it up the hood in Chandler Hall after actually going through some base washes. I did make VCl4. It's a red liquid. It's like titanium tetrachloride, very hygroscopic. It fumes. And as I'm taking this down with this nice precious amount of VCl4, I dropped the flask. And it started to fume in the hood, and I shouted out some expletive deleted. And Harry was walking by, and he looks, and what happened? I dropped it, and he said, quick, let's take its spectrum. and so we got a cuvette, we put some of this fuming stuff in, we went to the Carey 14, and Harry flipped the switch. I don't know what happened, but the strip chart recorder pen just pegged. And he looked at me and said, "You've got it, you've got it." And I said, "I had it." And it was shortly after that that Harry came to see me about going out to Brookhaven and doing a crystallography project rather than any more synthesis.
So tell us more about that crystallography project and where that took you in your research.
Okay, Harry gave me 2 samples of crystals and went to Brookhaven, and I met Jim Ibers there. We started to do the structures of both of these. One turned out to be nickel bis thiolene complex, nickel bis MNT. At that time, it took about 6 weeks or so to collect data, and this was done by photographs, and then I had to read the photographs, so look at each diffraction on the film and index it and estimate visually its intensity on a scale from 1 to about 80. You do this, you write it down, and then at that time they had key punch operators who would type in these numbers. It took a while, but we did get it, and this was actually, there were 2 structures. The second metal platinum hydride structure that was done was also part of that summer. And by the middle of my first year in graduate school, we had a communication in JAX.
So one of the topics you studied had to do with these metal dithiolenes, which you just mentioned, which was, I gather, a rather controversial topic then. What do you remember about those controversies at that time?
It was a very interesting time. It's important to remember Harry at that time was in his late 20s, and I was just 20. He had a significant group, and obviously everybody is in a competitive mode. There was a group of Gerhard Schrautzer, there was a group of Dick Holm and Alan Davison, Edelstein and Mackey at Harvard, and then there was Harry's group. And there were some fundamental differences of interpretation with regard to was it an oxidation on the ligand, was it an oxidation on the metal, was it, did you have, well, we never thought about things, at least I didn't, anti-ferromagnetically coupled and things of this type that we do today.
So do you want to take us forward from that time to when you started thinking about an independent career and when you thought about starting up your own program?
I think that working with Harry led me to the view, this is what I want to do. At that point, and this is 3rd year into graduate school, we started interviewing. There were a number of us. One of them was my colleague Ed Stiefel, who just passed away a couple of years ago. We were contemporaries and close members of the group. And we went out to interview. It was a process a lot simpler and I think less stress-inducing than the process today.
Did you try to reproduce the feel of Harry's group and the dynamic as well as extend the science, or was that just not something that would have been easy to do?
You may have tried to replicate what Harry could do, but that's not possible. I think it was important to build a sense of group, a sense of community, a sense of mission. And I did have a small group when I first started at Brown. One of those people was Court Pierpont, who's at University of Colorado. Another was Art Schultz, who was at Argonne, Don Vanderveer, and a few other people. We were doing mostly structural work at that time. So we were trying to make new compounds and then do their crystal structures. By that time, a computer-controlled diffractometer had been developed, so we were able to do some of those, but we also did some structures by film.
So maybe I'll use that as a jumping off point to ask you to talk about the role of technology and different projects in your research. It seems to me that you've used a broader range of techniques than many inorganic chemists have, and moved around a fair amount in different kinds of compounds and different kinds of technology.
A lot of what people do, in part, becomes a kind of follow-your-nose chemistry. And sometimes your nose takes you in places that you never expected to go to. If you wanted to do an ESR spectrum, you would do it. And if you wanted to do some dynamic NMR study, you did it. You didn't develop a network of collaborators the way I see young people today doing. In the course of this, I found interest in luminescence, and I found interest in NMR, and interest in structure, catalysis, and of course what I'm doing now today relating to solar energy.
So let's go back to your career path for a few minutes, if we can. You moved from Brown to Rochester fairly early on in your career. Can you tell us a little bit about that decision and maybe perhaps what you'd advise young scientists to think about when they're thinking about such moves?
Well, in terms of the advice is think carefully and examine each opportunity in the concrete, meaning the specifics, not a general "I want to move" or something like that, because sometimes the pasture is not greener on the other side of the fence. Sometimes you get there and you realize, no, it was pretty green where I was. The time, though, that I moved was the early 1970s, and at that time a lot of universities were in trouble in terms of running deficits. There was a tightening of the funding and a question of mission. And Brown at that time had said that they were going to focus on their efforts on being the outstanding undergraduate institution that it is. I interpreted that less emphasis on the graduate, and at that time Rochester was one of the best endowed universities with a brand new building and several leaders, academic leaders, who said we want to have one of the top chemistry departments. So that's what stimulated the move.
From that, though, I think it's also true that teaching is very important to you. It's something that you care a lot about. And tell us a little bit more about balancing the teaching and research. Clearly, you shifted your balance when you moved to Rochester, but teaching still remains very important to you, doesn't it?
It does, and it always has been. I think that one reinforces and informs the other. I think that teaching is a question of communication, and I think that research is a question of learning and creating new knowledge. So when you learn and create new knowledge, you need to disseminate it, and you need to teach it, and you need to explain it. That's one of the reasons why in many places teaching is a requirement. That is, we have our graduate students serve as teaching assistants. If you can, and I tell the students, if you understand something, you will be able to communicate it clearly. No matter how articulate you are, if you don't understand it, it's going to come out like mush. So it's really important, and I always find that one reinforces the other. I love the undergraduates, the enthusiasm that they have. The graduate students, it's just great. So.
Well, I'd like to return back to the move to Rochester for a minute, if I can, and what you found there, and how you wound up building the really remarkable program that you've enjoyed being part of for many years now.
One of the tasks when I went to Rochester and was to try to build an inorganic chemistry program. They didn't have one of any significance, and so the challenge was put forward. But the challenge did require continual pushing on my part, And it did require a confluence of a number of factors and an element of luck. But I think we were able to make some hires. One of those was George McClendon, who was at Rochester for 20 years. One was Bill Jones, who's still my current colleague and probably my closest friend in the faculty. Another, and then the three of us together worked to build Inorganic as a coherent strength within the department. Then we had Guy Bazan, and then after Guy left, we had Cara Brand and Pat Holland, and I think it's a unique strength.
A lot of schools have tried to do what you did at Rochester. Are there any pieces of advice you give to people about how to select colleagues, how to build a program that's more than the sum of its parts?
I think that what is critical is that you try and build a coherence and a sense of, maybe it's too small a group to call community, but we genuinely cared about each other and we did things for each other, and I think that was really important, and we had a good time doing it. I think that's really important. If there was a party, the inorganic chemists were always there.
Always. Today, there seems to be a great push in research towards research that has applications. And I guess funding is a key consideration here on all of this, particularly in energy-related research, which is what, of course, you do. What advice would you have for new investigators on formulating research ideas in this question of applied versus basic research problems?
It's a very interesting and it's a very good question. It's an important question. Today, I think there is greater emphasis from when I started on application. And this sometimes dominates in the thinking of new faculty and students who are just entering into their independent careers. And in the communication of our science, how many times have you talked with somebody from outside of chemistry whose response is, well, what good is it? Not why is it interesting? So we tend to think about application more today, and we tend to dismiss a lot of fundamental understanding by saying, well, chemistry is a mature discipline. I'm not sure that that's fully true. My advice to students, though, is, or to new faculty, is pick a problem that is important in the context of potential application, but pick a problem that also has fundamental interest. It's possible to do both.
And do you think your views on this have evolved over time? I mean, when you started your research program, did it have a different tenor to it as a result of the change? Has it changed?
Well, absolutely. When I started my research, I think the first things I did was make, trigonal prismatic complexes. We tried to make diselenoline ligands and selenium sulfur unsaturated ligands, and we really smelled up the place badly. But that was just, purely, let's see if we can make these compounds. I started to work in nitrosyl chemistry, and then it was a question of linear versus bent nitrosyls. Can we control that? So this is really fundamental chemistry structure. We did work on water-gas shift, but without thinking about the potential use of the water-gas shift reaction as a hydrogen-generating reaction, but rather, how did this happen? So my thinking at that time was much more focused on chemistry in the context of chemistry, not chemistry in the context of what can we use it for.
And do you think that's changed? Do you think your work more recently has changed?
I think so, in the sense of we want to make hydrogen because I think water splitting, well, first, I think water splitting is the key to artificial photosynthesis. I think that solar energy conversion is the most important problem that society faces, or sustainable energy for this century. Most important problem that is not directly biologically related. So I think solar energy is important, and I think that the conversion of sunlight into stored chemical energy is really most important. So within that context, yes, making hydrogen is important, but as we do this, we're trying to understand the details of the catalytic process, the details of the chromophore, the details of the system, and how you get the reducing electron from one place to another. So we are trying to keep a focus on understanding, but at the same time, we know that this is potentially useful.
So you've had a sort of an arc of different kinds of projects and wound up at solar energy and clearly been a major figure in promoting that as an important challenge for inorganic chemists. How did that all come about? Was it related to the industrial collaborations you had at Rochester and the emphasis on photochemistry there, or did it come from some other direction that you wound up in the solar energy area?
Yeah, the kinds of threads that go through one's career, and each of you will experience it as you do, are interesting. I remember, for example, Al Bard was talking about, let's say, photoelectrochemistry, so that you could do some electrochemistry and get light out. And this was with ruthenium, tris-bipyridine, and oxalate. And I was fascinated by that. I said, what's the most important thing you need? And he said, well, first you need a luminescent compound. So I opened up every drawer in the lab. It was dark, and I walked around with a dark light, and I found these luminescent dithiolene iridium, rhodium complexes, and then we looked at that for a while. And so we started photochemistry, and then we found these luminescent platinum dithiolate, these are dithiolene, and 1,1-dithiolate diamine complexes, and then was able to get support from the Department of Energy on these luminescent systems, and then started to consider the question of, well, where do we go with these? And one of the places was to try and separate charge, photo-induced charge separation, and then take the electron that you generate, the reducing electron, the oxidizing hole, and see if you could store the energy chemically. So that's how we got there.
My memory of first hearing your name, Rich, was when I was an undergraduate, I believe. I heard about your work on parahydrogen, and I was wondering if you could talk a little bit about that work.
It's an interesting story. It may go longer than the interview, but let me see if I can condense it. When I was first at Brown, there were two people, Harold Ward, Ron Lawler, who were working on chemically induced dynamic nuclear polarization, KIDNIP, and radical pair mechanisms, the same thing that was worked on by Gerhard Kloss at University of Chicago and Kaptein in the Netherlands. And so his unusual NMR resonances, enhanced absorption or emission. When Don Berry was a postdoc with me, we were doing some work with dinuclear rhodium complexes, and we were adding acetylenes, and it turned out there were some very unusual colors and kind of sage expression on my face. I said, Don, we should maybe look at these things really at very early NMR time. And I believe that Don may have seen this first, but then he left very shortly after that, and another postdoc took over the particular project. And we found that we could get really impressive signals by NMR. And so what we would do is we would sign up for NMR time at night, and we would leave the sample stored in liquid nitrogen over the day, and this was a rhodium complex with acetylene, and we would have hydrogen atmosphere, and figured that leaving it in liquid nitrogen overnight you know, nothing's going to happen. And so we did this, and we saw these wonderful signals, and we thought we had KidNip, but then we found out, actually, as we proceeded to eliminate different possibilities, it couldn't be. And then we heard about the work of a fellow at Caltech named Dan Weidekamp, where he had proposed that you get polarization with parahydrogen. So we huddled, we got back together, our group, and we said, let's see if we can prove this. And we did that. We just put some hydrogen in a flask, and we put some rust at the bottom because that works as a catalyst, and we dunked this whole thing in liquid nitrogen, and then we took the hydrogen and we put it in there, and we were able to observe the polarization. And from there we went on, and I really am very, very pleased that Simon Duckett, who's now at the University of York, he came to postdoc with me, and he was the one who really could take the NMR phenomenon and develop it the way he did.
Well, you mentioned earlier that the philosophy of collaboration has changed over the years, and I know you do more collaborations now, and you kind of witness collaborations of your former students and colleagues, and I wonder if you want to comment on that role in your own research or that broader role in modern chemical research.
I think there's a very important part with regard to collaboration and how the idea has evolved. To be honest, I think chemistry, unlike big science, physics, and with centralized facilities, was in some ways a cottage industry. That is, we each had our own organometallic laboratories, and we could do things. And that's what I said earlier. But I think mostly, beginning with the bio-inorganic chemists, they've established collaborations for doing many different techniques, and I think that's a wonderful thing. I think it's worked out pretty well, although you should know who your collaborators are. And I would say that to people who are developing their collaborations with specific individuals, do know them, share a common intellectual interest. Now, fast forward to somebody like myself now, who's more towards the end of his career, and I think there's a different role for collaborations, and that's what I'm trying to achieve myself. I think that we should be moving away from, as we get to a more exalted age, that we should be moving away from just being the principal investigator and tackling the role of being a co-PI and working with others. So I've developed a collaboration with Alison Frontier, who's a young organic chemist at Rochester, using some of the iridium chemistry that we developed in conjunction with her interests in organometallics for synthesis. And I think we've had some great success with Nazarov cyclization chemistry. Or with Dave McCammett, who's another young faculty member at Rochester, with regard to time-resolved spectroscopy and photoinduced charge separation and photoinjection into semiconductors. Or with Pat Holland, we're collaborating on the catalysis for hydrogen generation. So collaboration plays a role for young people, plays a role for senior people in different ways, but it really is important.
Well, I guess if I can sort of stretch you in a slightly different direction, as you become a senior person whose opinion is valued not only as a co-PI, but as an advisor to these large centers that have started cropping up over the years and on advisory boards. And is that a role that you find useful? Is that a direction that you think is a good direction for modern chemistry? How has that evolved, and how do you see it from your perspective?
Yeah, I'm not a complete fan of the very large centers, and even though I participate as an advisory board member in one, and that's the one that is directed by Harry Gray, the CCI for solar energy. that's very near, and the subject is very near and dear to me, so I'm pleased to do that. But I think in the scheme of things, this is a little bit top-down, and what it does is I think it forces collaborations. And I like to think that the best collaborations develop one-on-one, two-on-one, and they grow from the bottom. So I think that that's something that I'm not sure that I am fully enthralled by in the current funding picture.
I'm going to change the topic a little bit. Tell us about your first reaction when you found out you were being considered to be the editor-in-chief of the journal, Inorganic Chemistry.
Wow. I think that was the reaction. No. Actually, what happens is that for any ACS journal, there's a set policy for how you select an editor. And there's a committee that is formed. It does not include the editor who's leaving. And it's leaders in the field who get together and they put together a list, and they will send that list to the person who directs publications. At that point, a letter goes out to all the people who are on that list. Your name has been suggested. Would you be interested? And what else, other information would you want to provide? And so I was contacted and responded. I don't know how many other people had been contacted and responded at the time. This committee then gets together and they prepare a rank-ordered list. And then I received a phone call from ACS saying I've been selected to be editor if I would be interested in doing that. Excuse me.
So you said yes, I take it.
I think I said, let me think about it, because it is a big commitment, and there were some commitments that had to be made on the side of the university and the department and me and ACS Publications. And after a couple of days, I got back and I said yes.
Okay, so when you were thinking about becoming the editor of Inorganic Chemistry, did you think back to the early years of the journal in a way that you've been doing now to celebrate the 50th anniversary?
I think, I'm not sure that I went back and thought about the history of the journal at the time. Our community, as you know from our 50th anniversary, has changed. We've evolved, we've gotten much larger, we've become much more international. I also think we've moved outward as the inorganic chemistry footprint has expanded. And I always concerned about, what is it that ties us together as a community rather than just have, people on the fringes, whether they're organometallic or biological or materials, and how to keep them together. So I was thinking about that, and I thought that A, communication is important, as I said earlier. B, we are a community, and we have a common foundation. And so the communication within that community, I think, was important, and that's the way I think I thought about it at the time.
Do you have thoughts about how you put that vision into practice as editor?
Well, first, I appointed some really talented associate editors. So you guys.
Good setup, Jim.
But, no, I think we talked about that. If we start from the year 2001, we went to electronic submissions right away. We changed the layout, we changed the cover, we got a lot of interest from the community. We had meetings of the editors where we talked about how to deal with this particular problem of an increasingly larger footprint. And that led to doing forums. And these are samplers of subjects, overarching problems, and how we could get leaders in the field to write about that, both to attract the interest of people who normally don't look at inorganic chemistry, and to try to build the connections between, let's say, the more physical inorganic chemists, the more synthetic, the more materials-oriented, the more biologically oriented. So I think we've tried to do that, and all of this goes on top of what is essentially a freighter that takes miles and miles and miles to stop, and or to start. And that is the primary reporting of research in inorganic chemistry. So I think we've had success in doing this, and that has led to more people reading it. We now have many more people submitting papers from outside the United States than ever before. We've become a global community, and so I think this is all interesting. I'm not sure that it was all in my vision. I think a lot of these things are circumstances that happen, and you take advantage of them.
So how about some more of your personal reflections on your experience as the chief editor? You know, what have been the challenges you faced, and some of the things that have been rewarding for you?
Well, I think from a personal side, you wind up having a lot of people who know you, and they wind up asking your advice or asking for your opinion. And so that, of course, makes you feel good. But I think there is an element of this that I would say is service. And inorganic chemistry is my intellectual home. And when you can do service for the community of your intellectual home, that makes you feel very good. And I think we've achieved that. And there's a lot more to do. It's an interesting challenge in its own way. Yeah.
Do you see a way to make it more evident? I mean, it's a vision that I think we all share, that inorganic chemistry is the center of all of these interdisciplinary threads that are going on in chemistry, or many of them. And do you see that as something that the journal can try to capture more as we go forward? And is that one of the challenges of the journal going forward?
Well, I think, yes, I don't want to say it is the center of all of these interdisciplinary or multidisciplinary efforts, but it is a center and an active participant in. And this needs to be recognized not only in communication, not only in publications, but also in how we look at and how we hire faculty. So it's not just in communication, and but I think that we want to have, let's say, our discipline reaching out in many directions, and we want to have people within that discipline know the many different directions that are possible.
What do you think are some of the major challenges for the journal itself, and maybe more generally for other scientific journals going forward?
It's a great question, because it relates to strategic thinking with regard to journals. And honestly, Bill, I would defer to you, but I'll tell you my own thoughts on this. And this is from an old dog. I mean, basically, we're going electronic. And how you share this information is really progressing very rapidly. There's social networking now involved in scientific communication. And as you know, I'm not a Facebook member or a social networker.
I've tried to friend you, Rich. Why don't you respond to my invites?
But I think this is very, very important. What I would like to see, rather than us starting new journals, lots of them, I would like to see a lot of effort go into making the entire process absolutely seamless and effortless, so that when a paper is published and you are able to access it remotely, you're able to gather the references, you're able to store the PDF, you're able to put all of those references, that reference and any others, in your own database, whatever that happens to be, totally searchable, that when it comes time to take that information and put it in a new paper, again, seamless. That's what I would like to see. There are different applications, as you know, different programs, but they don't all, and they overlap, but they don't talk together. This is what I would like to see, but then there are the other parts about reading a paper and saying like, dislike, you know, send it to your buddies. That I haven't gotten into.
The journal is celebrating its 50th anniversary, and you've clearly thought a lot about that, and I wonder if you can share that with some of the viewers, what you were thinking about going into the 50th anniversary.
This was a great experience for all of us. I think you guys will agree on that, and I hope that all the other people who participated would as well. We had an opportunity to have a 5-session symposium, and we had a really remarkable collection of speakers, and we covered areas from energy, biological, bioinorganic, materials, supramolecular assemblies, fundamental spectroscopy, photochemistry. It was just a wonderful assortment of science, and all with a clear inorganic footprint or foundation. So I think the 50th anniversary was able to allow us to appreciate just how broad our field is and just how impressive all the work has been, both in the past and recent. I think that says a lot. I know that I've said before, we're also an international community. So it's a really wonderful thing. Bill and I participated in a trip to China, and we had a wonderful time. And the papers from China are the second largest contribution to inorganic chemistry today. So we're a global community, and we have a great breadth of science. And to be able to highlight that in our 50th anniversary was a wonderful thing.
So tell us a little bit how you came up with this idea of doing these interviews, and maybe perhaps you can tell us a little bit about what you found most memorable about doing them.
Interesting question. Actually, chemistry is a story of science and the people who do it. I found that the science is written in the papers we publish. But I don't want to sound like Dow Chemical Company. What is missing was the human element. And I think that it was important to try to not just have people write an autobiography that nobody would read, but rather that people get a chance to use all the means of communication that we have today to be able to show what they're thinking, what they're feeling, what their motivations were, and to be able to use that for not just archiving, but for our students, college students thinking about going into science, for high school students. And so that was the motivation. I was really saddened when Bob Parry passed away, when Al Cotton passed away, when Fred Basolo, when Henry Taube. These were giants in our field. And we didn't have a record of having them talk in an informal conversation. And so that was a motivator. and that started me off on this. I think it's been fun for the people who have been interviewed, and
How about for you? Has it been fun for you? What do you find? Do you have any memories from doing these interviews that you'd like to talk about?
Well, I think that I have learned about people, and I think that people who listen to these and watch these interviews will learn, and they'll find the motivations. You know, Harry Gray or Fred Hawthorne or Dick Holm, they're leading figures in our field. But it's important for young scientists, students, how did you begin in science? What moved you to do what you do? Was it a chemistry set? You know, was it an older brother who did this? I think these are important. And then also in the course of this, you see the thinking that makes these people who have been interviewed, I'll leave myself out, who have been interviewed, what makes them so successful.
Well, and the different personalities.
That's right.
People who've been successful.
That's right. Absolutely. So it's a story of science and the people who do it.
As you look forward scientifically, clearly, as you said earlier, the challenge of sustainable energy is very important to you, and you see it as an important area. Can you comment on the role of chemistry and the role of inorganic chemists in that grand challenge for us?
Well, I think in the chemistry problem, inorganic chemistry will play a major role, has to play a major role. From the standpoint of people who are focused on molecular science, we think about charge transfer, photo-induced charge transfer, the ability to take an electron from here, let's say water, and put it over here to make hydrogen. And so how do we do that? Well, it all starts with a chromophore, a light absorber, which is in general some kind of charge transfer state, and metal complexes are good for that. You have a catalyst out here, metal complexes are good for that. You have another catalysis that's going on over here where you're pulling the electrons out of, metal complexes are good for that. You have the question of durability, and so semiconductors could play a role, and that's inorganic chemistry. There are lots of different aspects of the artificial photosynthesis question in which inorganic chemistry will play a role. Let's talk about photovoltaics. Okay, so what do you use? You're using silicon, you're using cadmium telluride, you're using copper, indium, gallium sulfide. Have I heard carbon yet? No. I mean, basically, we may think about these as materials, but materials are inorganic compounds. So I think inorganic chemistry plays a key role, and even if you are a physical chemist, physical scientist, or a physicist, it really behooves you to learn your inorganic chemistry.
Well, Rich, I think we both really want to thank you for sitting with us and sharing your thoughts, and thank you especially for your leadership of the journal that we both very much enjoyed.
Yeah, thank you very much, Rich.
Okay, well, thank you, guys. I have enjoyed this, and now I see that being on the other side of the microphone is a lot of fun, too.
Good.